So now we'll see the concept of the stream function. In the case of the two-dimensional incompressible flow. So two-dimensional incompressible flow, if you see the concept here, just come back to the, what does it mean by the incompressible flow? Again, recapitulation one more time. That is the divergent of velocity vector is equal to 0. See, in any coordinate, whether the coordinate is the Cartesian coordinate or polar, cylindrical polar coordinate or spherical coordinate, wherever it is, this is always satisfied, this equation. So here, in case of the Cartesian coordinate, we know the two-dimensional is xy we are considering. And the velocity vector is the u is along x-axis and v is along y-axis. So divergence is the, the divergence for the Cartesian coordinate is the I del x plus j del y. So this will gives you the equation. If you dot product of these two, it will gives you the equation del u del x plus del v del y is equal to 0. So this is the equation for the two-dimensional incompressible flow, is the continuity equation. How it is a continuity equation? Because if you remember from the control mass system, the continuity equation we solved, where we get this thing 1 by rho, the total differentiation of the with respect to the time of the density, that is plus 1 by v dv dt. So that is nothing but the volumetric strain rate, which is for del v is equal to 0. So in the case of the incompressible flow, this term itself 0, so this is also becomes 0. So each term is 0. For the case of the incompressible, as this is 0, so this also becomes 0. So either you can write it the continuity equation. So the same equation will gives you the continuity equation for the case of the incompressible flow. That's why this equation is much more important in that cases. So again, I'm rewriting this thing, the continuity equation, del u by del x plus del v by del y is equal to 0. Now here, let me consider one separate function. Let me consider one function psi. How we can describe this psi? U is equal to minus del psi by del y and v is equal to del psi by del x. Now if you put this thing in this equation, you put the u and v in this equation, what will comes? It will comes in this manner. So d square ru by dx by dy plus, sorry, this is a psi function, and del square psi dy by dx is equal to 0. So that means this term and this term will be equal. At what condition is this two will be equal? When the psi function is a continuous function. From mathematical expression, we know the psi function is a continuous function. Then only these two will be equal. This term 1 and term 2 will be equal in that cases. So some function we have defined that is a continuous function. But why it is telling the stream function? For that purpose, we consider the psi function is in a Cartesian coordinate, it is depends on xy. So change in the function, d of the function, change in the function. So how we can write it in terms of the partial differentiation form? In this way, this manner. So del psi by del x into dx plus del psi by del y into dy, as it is a function of two variables. So partial differentiation mode, we are writing it here. Whereas this term is nothing but the v, and this is nothing but minus. So if you write it down, v dx minus u dy. Now, where this function is a constant, no change of this function, at where? So psi is a constant. If we consider, so del psi is equal to 0. So del psi is equal to 0 means this becomes is equal to 0. V dx minus u dy is equal to 0 at this condition. So in this case, we are considering where the phi is equal to 0, phi is equal to constant. So in that case, if you put this value, so v dx minus u dy is equal to 0. So you are getting the equation dx by u is equal to dy by u. This equation is a streamline equation, two-dimensional streamline equation. This case of the two-dimensional. So this is two-dimensional streamline equation. That's why this psi function is known as the stream function. That's why this psi function is known as the stream function. So along a streamline, this function is a constant. Psi is constant. So along the streamline, if you consider the streamline, along the streamline, the psi value is the constant. So again, we rewrite this thing, whatever we are discussing, we rewrite this part. So psi is a continuous function. Psi is constant along a streamline. Next thing, the psi exists if the flow is incompressible. If the flow is not incompressible, the psi does not exist. And two-dimensional, of course. So psi exists only if 2D incompressible flow. The psi is only exists only if two-dimensional incompressible flow is considered. In that case, where the u, the velocity along x-axis, is minus del psi by del y, and v is equal to del psi by del x. Here considered. So this is the bullet point we are talking about in here. Now you see the physical significance of this psi, because we have already told that along the streamline, these are the streamlines of a flow. These are the streamlines of a flow. So each and along the streamline, there is some constant value C1, along this phi C2, along this phi C2, psi C2. So psi is equal to C1 along the line. Throughout the line, the psi value is the constant. Here also the throughout the line, the psi value is a constant. Here also the throughout the line, psi value is a constant. So that is the condition of here. We are defining the psi in this manner. Now the volume flow rate, how it is connected with the stream function. Before telling again, one thing I'm stressing here, that is that here two-dimensional case, two-dimensional incompressible flow, only the psi is existing. If it is three-dimensional case, it will not exist. So here the equation u and v is a Cartesian coordinate. If it is in case of the polar coordinate, the polar coordinate, cylindrical polar coordinate, if you consider. So polar coordinate, if you consider, the same equation will comes in the different manner. So polar coordinate means r theta, radius and theta along. So along r, the velocity is the vr, along theta, the velocity is v theta. So this is the vr, this is the v theta. So So VR you will consider in that cases minus d psi by r del theta. And V theta you will consider del psi by del r in this way. The same one, because that is the in cylindrical polar coordinate. VR and V theta we are taking it in this way. One example we will see later regarding the polar coordinate. But what is the physical significance of the stream function? Stream function, how it is related with the volumetric flow rate. This thing we'll see now. So we come back to the here, the how it is connected with the volumetric flow rate. So let you take 2 points. One point is A, that is a fixed point. Another point is taken as a B. That may be an arbitrary point. So about A to B, across these 2 points, if you join by a line, what is the flow rate? What is the flow rate? Volumetric flow rate about the line, across the line. So that we are going to consider. So in that case, if this A point and B point lies on the different streamline, if the point A and point B lies on a different streamline, there must be exist some volume flow rate. So let you take it is a some phi 1. This along the B point is at some different phi 2. So there must be some volume flow rate. There must be some volume flow rate. And what would be the volume flow rate? The volume flow rate Q, volumetric flow rate Q dot. Q will be equal to the psi 1 minus psi 2 mod of, which is bigger, mod value. Psi 1 minus psi 2 into the perpendicular width. The perpendicular distance with the width we cannot see here. The third dimension, perpendicular to the plane. So this value will gives you the volume flow rate. How it is coming? We'll see now how this value is coming in this way. The volume flow rate. So to consider this thing, you have to take one small element, DL. Small element you are considering DL. So what is the flow rate across the DL element? Like this element. This is a bigger version of it. DL, one differential element we are taking here. So DL, so here you take, that is the dx and this is the. So DL is the dx and dy. Here that is a theta. That you take on a theta. So it's like a triangle. So along x-axis the velocity is, that is the u. Along y-axis the velocity is v. So along x-axis velocity u, along y-axis velocity is v. And volumetric flow rate. So volumetric flow rate is velocity v dot dA. That is the. So area is a vector we are considering here. Area is a vector. So about the area, if you draw the normal line, about the area, if you draw the normal line. So just like here. Here, what is the area? Here, area is this dy into w. W is the width. We cannot see the portion. So what is the area of this portion? So v is along the area. So here, area is the dy into width. That is the area. And from the area, if you draw perpendicular, so I is along I. Area. Similarly here, dx. Here area, magnitude of the area is the, in that zone, if you consider in this zone, the magnitude is dx into w into dx. Area magnitude. And area that is the minus J. Minus J axis. So J cap minus. That is the area. So here, what is the flow rate is coming in? From both sides, the flow is coming in. So total flow rate about this here, if you consider small dq, flow rate about this small elemental area. That is nothing but it is coming in that side, it is coming the velocity v into sorry, it's I, v into I, minus v into I. So I is a minus because velocity here, if you magnify this thing, this element, if you consider, you give the name, it's a better thing. A, B, and C. If you give the name, AB is the DL. AC is DY, and BC is the. Now here, how much flow is coming inside? So that much flow is going out. So from along this axis, the flow dq is going out. The flow rate dq is going out. So what is the dq? Because whatever the coming through the dx and dy, that much flow is going from the dl. That is the basic concept. So whatever the flow is coming about this area and this area, this much of flow is going out. So how much it is coming inside? So about B, QBC. So Q through BC, this part, how much flow is coming? So there the velocity is here it is a U, sorry. Here U is the V. So the velocity is coming here about the BC is the V into J. So V is the velocity and minus J is the magnitude. So V magnitude into to the direction. That of dot product of this area. Area is the minus W dx into J. Minus W dx into J. So QBC is coming in here. So what is coming here? So J will be minus, or minus also become plus. So it will come as a V dx into W. That is a QBC. So del QBC, very small amount. So dq dot, which is coming out from the AB, the same dq dot which is coming through the BC plus dq dot coming through the AC. So from the AC, how much flow is coming in? From the BC, how much flow is coming in? The same flow is going out across AB. That is the consideration we are taking it here. So through the BC, how much it is coming? V dx into across this part. If you consider across AC, how much flow is coming? So here, if you consider across AC, how much it is coming? So dq of AC. So V dot dl, V dot dA. So what is the velocity? Velocity is here along AC. U is the magnitude and minus I. Because it is a negative x direction is going. That is the velocity. So velocity dot product of area. Area is the dy w with into I. So this will gives you the minus u dy into w. So it is coming as a minus u dy into w. So the flow rate across the small elemental area AB. So V dx minus u dy into V dx minus u dy. We have seen the previous cases, just few minutes back that d psi will comes in this manner. D psi of dx plus d psi dy of dy. So it is nothing but v dx minus u dy. It came like this. So about this small elemental area across this way, the flow rate is d psi into w. So what you are getting it, I just from this concept we just writing it down, the last part whatever we are getting it, and do the integration afterwards from psi 1 to psi 2. If you do the integration over this point, so across this total from, so total flow rate about AB, this is small. This AB we are considering is a small amount. It's not the same like this. Just we are taking one small part of it. Small part of it. And in this way, just it is the DL, and this is dx, and this is dy in this way. So that is equal to the integration of width into d psi, where psi is varying from psi 1 to psi 2, or you may be write it psi 2 to psi 2. Width is not a dependence over the psi. So width will come out, and your equation is come is the psi function 2 minus psi function 1. So that would be the flow rate, volumetric flow rate across the streamline. If it is the same streamline, no flow. If you consider A point here and B point here, so across AB, there is no flow rate. So along the same streamline, there is the no flow rate. So the 2 points should be in the different streamline. Then only you will get the volumetric flow rate. And the value of the flow rate will be anything. That would be same always. That's a width multiplied by the difference between the stream function. If the B point, instead of here, if it is at here, the same value. So about the AB, the same value you will get. The value will not change. Flow rate value will not change. If the B is at here, the flow rate value will never change. So here, the flow rate across this line, across this line, across this line are the same. No changes. Because psi 2 is not changing and psi 1 is also not changing. So this is the fixed point. The B may be the variable point. If you keep the B as it here or any place, any location of the streamline, the flow rate value will not change. On the same way, if the B is at the same streamline where the A lies, then the flow rate becomes 0. That is the physical significance of the stream function. So in the short, we are writing it down. The volumetric flow rate, if you're asked, and if you're asked here about the volumetric flow rate, so it will becomes the Q across the 2 point AB or any value 2 point, that would be width into psi A minus psi, where the A lies and A lies, the stream function. That will gives you the volumetric flow rate. The physical significance, the A point and B point should be in different streamline. If it is not in different streamline, same streamline, volumetric flow rate becomes 0. So that is the case. It's better to write the mod values because the flow rate values should be positive. That's the way. So here we are finishing the stream function concept. The concept of the stream function only for the 2-dimensional incompressible flow. This concept only and only if exist for this kind of the flow. Two-dimensional incompressible flow. Now another concept we are taking it, velocity potential function. Velocity potential function, this is another function, the phi function. Previous one was the psi function. This case it was the psi function, now it is a phi function. Phi function is a, we can write it in this way, is a function of, it's also a continuous function we are taking. It's also a continuous function. But the beauty of this function is okay. The velocity potential function we will see now. This function only if exists whenever the flow is an irrotational flow. It may be for two-dimensional, it may be for three-dimensional. It does not matter. But this phi function, velocity potential function, only and only if exists when the flow is irrotational flow. So irrotational flow, what is the concept? So we have told the concept of the vorticity. The vorticity is zero. The vorticity vector is zero for the case of the flow. Vorticity vector, what was the vorticity vector? That is the curl of V is equal to zero. Curl of velocity vector is equal to zero. On the previous case, the divergent of the velocity vector is equal to zero because incompressible flow, so divergent of velocity vector is equal to zero. In that case, the curl of velocity vector is equal to zero. So curl of velocity vector, if zero, then we can write it down. The V is a grad of any function. V is a grad of any function. Because the vector identity, this is always zero. This term is always zero. How it is zero? Because grad value, we are considering the velocity is grad of a function. What does it mean? I d psi by dx Cartesian coordinate, d psi by dy plus k d psi by Lz. Okay. On the same way, if you compare this thing in the Cartesian coordinate, IU, JV, KW. So U we are comparing with del phi by del x. V we are comparing with del phi by del y. And W we are comparing with del phi by del z. We are comparing with it. Because the same, this is equal to with this, the second term is equal with the V, and third term will be equal with the W. So here we are considering this thing. How it becomes a zero? Because the curl of this function is a zero. How it is a zero is coming. This thing, the vector operation, if you want to see, I will show you. So we are telling about this. This is a zero, vector identity. How it becomes a zero? So you have to take the curl of it. So curl is the I, J, K. It's a del del x, del del y, del del z. And d psi is a d phi by dx, d phi by dy, d phi by dz. If you go for the curl operation of it, you will get this thing I under del del y of d phi dz. So it will comes in the del square phi dy dz minus del del z of d phi dz. So del square phi by dz. If the phi is a continuous function, if the phi is a continuous function, this is equal to same. Both are same, so it becomes same way. If you consider the j, so j is a d dz of del phi del. So it is coming as the del square phi del z del x minus del square phi del x del z. So ultimately it is closing to the null vector. K del square phi del x del y minus del square phi del y del x. That is also the same. So ultimately, this becomes a null vector for the case of. So it is matched with the irrotational concept. Because irrotational value, irrotational concept is del phi, the curl of the velocity vector is equal to 0. So we can compare the v vector with this term. We can compare, it is easier to compare this velocity vector with this potential, grad of phi. So that's why you can write it. The velocity vector is the grad of a function. And this function is known as the velocity potential function. This function is known as the velocity potential function. So velocity potential function v is equal to where the phi is a velocity potential function. It is only exist, velocity potential function only exists for irrotational flow. This is the repetitively I am telling this thing because it is much more important here. Whether the flow is 2-dimensional, 3-dimensional, it does not matter. But the flow should be irrotational flow. Then only this is exist. This velocity potential will be exist. Whereas in the Cartesian coordinate, u is equal to del phi by del x, p is equal to del phi by del y, and w is equal to del phi by del z. Now our consideration is 2-dimensional irrotational flow. 2-dimensional. So 2-dimensional irrotational flow is, this is the equation. U is equal to u and v, only these two we are considering. Only these two we are considering here. Okay. Now, to exist, how the flow should be exist, or the existence of the flow, how we could know the flow exists here. If the flow satisfy continuity equation, if the flow satisfy continuity equation, then only we can say the flow exists. Otherwise, there is no meaning of the flow. If the flow does not satisfy the continuity equation, the flow does not exist. So next concept, after telling the velocity potential, the concept we are taking 2-dimensional incompressible plus irrotational flow. So we combine these two concepts, how it is. So before combining this thing, we just writing down u is d phi by dx for the case of irrotational flow. So we can write the same u as a del psi by del y for the case of incompressible. From the irrotational flow concept, we are getting this thing. From the incompressible flow, we are getting this. So here, two-dimensional incompressible flow plus irrotational flow is considering here. So U is del phi by del x is equal to minus del psi by del. As it is incompressible, so psi exists. As it is irrotational, so phi exists. Similarly, V is equal to del phi by del y, and that is equal to del psi by del x. It is as in case of the two dimensions, so W is not existing for the case of the phi. Already psi, there is no existence of the W, and phi also no need here. So this equation is known as the Cauchy-Riemann equation. Cauchy-Riemann equation. This two. What does it signify? It signifies that thing. So let you take first case, case one. We are taking two cases here. Case one first. Case one, it is a irrotational flow. So as it is a irrotational flow, psi exists. Phi exists. Sorry. So phi exists means there is existence of the phi. So it satisfies that there is no rotation in the flow. Now, if we merge this concept with the incompressible flow, compressible. So incompressible flow means du dx plus dv dy is equal to 0. So as phi exists, irrotational, first we are taking irrotational flow. First condition we are taking irrotational flow. So phi exists. So U is equal to del phi del x. V is equal to del phi. Now in incompressible flow equation, if you put it this same equation, U is equal to del phi by del x. So it will come del square phi by del x square plus here del square phi by del y square. If there is it's not a two-dimensional, it may be three-dimensional, so W terms will come, and as well as here dw by dz, so another term might have come. But we are taking two-dimensional, it's better to signify it. So that is equal to 0. This equation is a del square operator of phi. Because del square operator is I of d square dx square plus z into d square del square. This function is a Laplace function. Laplace equation. This equation is a Laplace equation, is a Laplace operator. So this is the function of a harmonic function. It's a harmonic function. Phi is here. So for the case of the irrotational plus incompressible flow, so we are getting the Laplace equation. Here we are getting the Laplace equation. What is the significance? There is a, from this equation, if you solve the equation and two solutions might have get, you got two solutions, phi 1 and phi 2. You are getting two solutions, phi 1 and phi 2. So del square phi 1 would be equal to 0. Del square phi 2 would be equal to 0. Same way, del square phi 1 plus phi 2 will be also equal to 0. That is the beauty of the Laplace equation. It is valid for the harmonic function case. That is the case 1 we are talking about. Same thing. First, you consider the case 2 here. You are considering the case 2. First, you are considering two-dimensional incompressible. Previous case, we are considering irrotational. Here, we are considering two-dimensional incompressible. First, compressible. So, two-dimensional incompressible means it is valid for divergent of v is equal to 0. So, it is simply we are writing it du dx plus dv dy is equal to 0. That is the first equation. So, from here, we are getting u is equal to minus. So, it is telling that psi exists. It is telling that psi exists because it is a two-dimensional incompressible. So u is equal to del psi del y, v is equal to del psi del x. Now here we are putting this thing in irrotational equation for two-dimensional cases. Irrotational for two-dimensional, 2D irrotational cases. So irrotational means curl of velocity vector is equal to 0. Curl of velocity vector means I, j, k, d dx, d dy, d dz. U, v, and so. U, v, and so. Here, actually, there is a two-dimensional case, so there is no existence of z also. So this part also would be 0. So this part we can rub it also. So this part also becomes 0 because there is a no existence of the z. This is also 0. So this equation, if you taking this thing, so what would be it if you go for the, so k only valid, because if you see I, so I is equal to del y of 0 minus v into 0. 0. Z is equal to 0 into u d dx of 0. Both 0. So only k is existing. K. About k axis. So k axis about. So that is coming dv dx minus du dy. That is equal to 0 for the irrotational case. That is equal to 0 for the irrotational case. So dv dx minus du dy is equal to 0. That is the irrotational flow, two-dimensional cases. Two-dimensional cases, irrotational flow. Now here you put the equation v is equal to del psi del x and u is equal to del psi. So v is equal to del psi del x if you putting at here. So d dx of, so it will comes del square psi dx square minus again. So minus here also minus 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 it becomes plus, and it also del square psi dy square is equal to 0. Same you will get back the same Laplace equation for the stream function. So stream function and velocity potential function, previous case velocity potential function is satisfying the Laplace equation. Here the stream function is satisfying the Laplace equation. The same condition, that is nothing but the Laplace equation. So it's a harmonic function, and as well as we can say if the solution, some solution is getting phi 1 and phi 2 by solve this equation. So then also we can write it psi square phi 1 is equal to 0, psi square phi 2 is equal to 0, and same way psi square phi 1 plus phi 2. So both the cases, case 1 and case 2, both the cases we see the, in the previous cases the phi is satisfying the Laplace equation. Now in that cases the psi is satisfying the Laplace equation. Now we are considering one more thing here. After this concept, the Laplace equation concept, what is the actually slope of the curve? So individually, we are taking the slope of this curve. This consideration is the last consideration of this part here. So the consideration is a two-dimensional incompressible and irrotational flow. So two-dimensional incompressible and irrotational flow. So along a streamline, we know along streamline phi is constant. This psi is constant. Sorry. So d psi is equal to 0. So d psi is, what is the d psi? D psi is, we have seen, del psi del x of dx plus del psi del y of dy is equal to 0. We are considering this is as a v dx. This is the minus u dy is equal to 0. So dy by dx is equal to v by u. That is the slope of the streamline. So for a streamline, any point, xy coordinate, any point, if you take, what is the slope of it? The slope is v by u. The slope at any instant of time, any point, the slope is v by u. The slope of a streamline. Now, next concept, where the phi is constant. Where the phi is constant. So phi constant, the same way, the phi constant means d phi is equal to 0. Along the line, the phi is constant. This line is known as the velocity potential line. Velocity potential line. The two-dimensional case we are considering only here because of the slope purpose. So the same way, del psi del x dx plus del psi del y of dy is equal to 0. So this means u dx. This means plus v dy is equal to 0. So here, dy dx is equal to minus u by v. Here it is for the case of the streamline. This is the case of the streamline. This slope is for the velocity potential line. Minus u by v. So there is a slope of the velocity potential line. So the slope of streamline into the slope of velocity potential line is equal to v by u into minus of u by v. So v will be cut and u will be cut. It becomes minus 1. Hence we can say the streamline and velocity potential line are orthogonal. Orthogonal to each other. This streamline and velocity potential lines are orthogonal to each other unless u is equal to 0 and v is equal to 0. In this equation, if v and u both are 0, that means stagnation point. This means stagnation point. The point where there is no velocity is known as the stagnation point. So this equation, so we can write it again one more time. So the slope of streamline into the slope of velocity potential line is equal to the streamline slope is v by u, and velocity potential line slope is minus u by v. If u is equal to 0 and v is equal to 0, this equation will be a infinite, unknown, indefinite. We cannot define this values. 0 by 0 into 0 by 0. It will become a 0 by 0 into 0 by 0. Undefined. If both are not equal to 0, then the slope is equal to minus 1. So u and v should not be 0. So this better to write is a streamline and velocity potential lines are orthogonal to each other. Except the stagnation point. That means u is equal to 0 and v is equal to 0. So it seems like that, and both are existing for two-dimensional cases because streamline and velocity potential. So velocity potential line is, if it is a streamlines, so phi is equal to c1, phi is equal to c2, phi is equal to c3. Then the velocity potential line will be like this. This is the phi is equal to some values, c dash, phi is equal to c double dash, phi is equal to c triple dash. Both are orthogonal to each other. So this is known as the flow net. Flow net. If you plot this thing, it is a flow net here. So that's all the concept in here. So here we finish this portion kinematics. Next, we'll see the problems regarding the kinematics chapter, which is coming in the GATE and other exams. So nearly all the types of the problem we'll see the next lecture onwards. Thanks for